All right, so we are recording now, so everything you say has the possibility of winding up on YouTube one day, or at least just in our files. So, everybody, again with us this evening is Tony Colaprete. He's the principal investigator for the LCROSS mission, which, as we all know, bombed the moon in October. He'll probably give us a little bit about that and tell us, no, we really didn't bomb the moon. And then he'll also tell us about the really exciting results from LCROSS, some really good stuff coming out of that. So with that, I give it to you, Tony.
Okay, thanks, Andy. Can everyone hear me this time? Good, good. That was not a conspiracy the last time to suppress results. It was my incompetence working a web stream. But I've gotten smarter thanks to Andy since then, and it's nice to be back now, about 3 months after the impact, to actually be able to catch our breath and say a little bit more. Um, yeah, so presumably everybody is familiar with the LCROSS mission and how we landed. We like to say landed on the moon, and it was an abrupt end to our landing. But we have been working on the results very hard. And what I thought I'd do is also talk about some kind of the. Somebody asked me actually in a staff meeting the other day about writing a blog regarding what goes on with the science kind of behind the scenes and with a mission like this or any other mission, but this mission in particular regarding the data. And a lot of people figure you got your data, then you start analyzing it and you get your answers. We have certainly a rate from the get-go, basically. After impact, one of the first things we actually do is assess the quality of all the data. And that actually takes a lot longer than you think. You can have all the tools in place and think you're you're ready to do everything, but you've got to actually go through and make sure that all the data has got high quality. Um, and in particular, one of the reasons we do that is all of our data is eventually, of course, released to the public through the planetary data system, and we have a project requirement to do that. And for LCROSS, that was 6 months. The requirement is that 6 months after impact, we release all of our data. And so a good part of our team, actually, and our team is, again, very small because it's a very small mission, is working on validating that data and preparing the PDS delivery. In particular, Mark Shirley, who is the lead software engineer, he was in the Mission Operations Center working the payload console. Kim Aniko is the payload scientist. Jen Heldman and Diane Wooden, they're all a big part of their time. Some of them, most of their time, is working on just making sure the data is properly calibrated, as best it could be, properly formatted with all the proper headers and everything else, so it can be delivered to the PDS. And that actually takes a lot of time and effort, but of course it's really important. Then the other side of the equation is really then, okay, understanding all those things you didn't expect in the data, and that actually for us on LCROSS has been, of course, the funnest part, but actually taken a lot of time. This data set was a lot more interesting than we actually had thought it would be. So that's what we've been doing in 3 months. And I repeat 3 months just because it's only been 3 months. It seems like it was a long time ago for me, and but it was really only 3 months ago. And we just actually, I submitted my lead, the paper I led to Science. I believe yesterday it was when I hit the submit, or the day before when I hit the submit button. And it's one of 6 papers that are going in as a set of companion papers for review into Science. That all relate to the initial results from LCROSS, and they are articles being written by LCROSS investigators as well as LRO investigators. And we have a great number of abstracts in at LPSC coming up, and I think we have 7 oral presentations, and I think I counted 11 LCROSS posters, and So certainly the results are going to be coming out more and more. We are working potentially to release the data to the PDS at or around by or around LPSC in early March. Our requirement is April 9th, but we think we can exceed that, and it's really a question of whether or not the science team feels comfortable enough releasing the data prior to them getting all their first papers submitted. So that said, I can kind of jump into some of the basic results. Actually, the other day, Tuesday, I gave a presentation, an hour-long presentation to the LCROSS internal staff. It's probably the second to the last staff meeting we'll have on LCROSS as we wind down, and presented some of the basic results from across the team, both ours and LRO results from the observation of the impact. Like I said, we've submitted to science, and we are technically in an embargo now, regardless whether or not it's accepted or edited or what. That said, I've had several conversations more closely with the editors of science, particularly the planetary science editor, and she's been exceedingly understanding of the position that LCROSS is in terms of having to get results out quickly. I conferred with them actually prior to our press briefing back in November, and they've given us really quite a bit of latitude, and I think sometimes they get maybe a bad rap for holding too close to or enforcing some really stringent embargoes. That doesn't seem to be the case, certainly at least with the LCROSS data. So I feel comfortable presenting a lot of the results, although, again, I'll be, before they go through a peer review, I'll be a little bit cautious, and I certainly I'm anxious to see the reviews and see how well all these results stand up against, sharp scrutiny. One of the most interesting things, and there's a couple ways I can go through presenting this, but I think there's a couple things that really surprised me, and I think that's a good way to describe some and get into some of the discussion of the data, and then I can leave it to the question and answer period to get into some more detailed questions. But there were a couple of things that really surprised me, and one of them was right at impact. At impact, we saw basically very little to no flash from the impactor. We knew it would be dim because it's a slow, low-density impactor, but we didn't see the visible flash with a very sensitive instrument, and we saw a very delayed and muted flash in the near-infrared flash detection. And that's very interesting. There's several explanations for that. One of them is that the impactor was essentially buried. It did not couple with the surface. It actually got buried in the regolith, and all the energy was deposited at depth. We all think that's pretty unlikely. And so more likely is that there's quite a bit of volatiles in the vicinity that actually took a lot of the energy in the impact and converted it into phase change. We're actually, Pete Schultz and Brandon Hemley and a couple other folks, Mark and Kim, are at the vertical gun here at Ames today and tomorrow, doing some follow-up experiments with some of our engineering instruments to test some of those theories, actually. So that was the first surprise. And the second surprise was that the morphology of the plume never showed donut shape, and we understand that, and it wasn't so much that it didn't show that morphology that we might have expected from a classical impact, because there was reason to believe from Pete Schultz experiments that it would have what we call a high angle plume, where a plume comes up at a very high angle straight up, and then there's another lower angle plume that comes up and moves out. That high angle plume can fill in the middle of the donut, the lower angle plume, and make it look just like a big washed out circle or disc. That wasn't what was necessarily very surprising. What was surprising was we saw dust suspended over the target. Suspended is not the right word. Dust still settling over the target all the way through the 4-minute flight that we had. So we saw dust from the get-go after impact, maybe just a couple seconds, so even less than that after impact, dust entering sunlight, and then we had signal of an ejecta curtain, debris curtain, all the way down, in particular in our spectrometers very clearly, all the way down to impact. And so we flew through the dust, what was remaining there. And that was really corroborated with some diviner measurements that are being reported in the science paper. LRO made observations right at 94 seconds after impact, and um, so they made some great observations, the diviner instrument LRO of the ejected cloud as well, and their visible channels, as well as the impact crater itself. So that was really surprising to me, and also fantastic though, because it really meant we had good signal on our spectrometers all the way down to impact. Um, the uh, the third, I think, biggest surprise for me was all the stuff that came up out of the hole, and it came up out of that crater, and how quickly it came up, and the variety of things that came up. And maybe in hindsight, a lot of people will say, "Well, you should have expected that. You hit some place that was about 45 degrees Kelvin. It's a good cold trap." But I think everyone was really and still excited and a bit surprised about all this stuff that we threw up there. Um, some of it I feel very freely talking about that isn't ours because it was presented at AGU, but the LAMP instrument that Randy Goldstein, Goldstone is a PI from Southwest Research Institute, he made measurements on LRO. What they did was they tilted the entire LAMP instrument, our entire spacecraft, LRO spacecraft, at the limb, so they could observe the impact plume with the LAMP slit, which is about 20 kilometers tall. So they flew by, and if my head is the plume, the idea was, and the slit goes between my fingers, they'd fly by the plume, basically like so. And what that allowed them to do was actually measure vertically, and as a function of time, any kind of vapors or whatever that came up. Now their observing footprint was basically between 20 and 40 kilometers above the surface of the crater. So they were looking very high up, and they saw a vapor cloud enter their slit and really pretty much fill their slit very quickly, almost instantly, relatively speaking, at about 23 seconds after impact, uh, and remained there for basically the entire flyby that they did. The What that corresponds to is a hot vapor cloud of about 1,000 degrees rising up very fast and into the field of view of the LAMP instrument. Randy's reporting on this in a paper submitted as part of this set to Science, and as he described at AGU, they've got a relatively good fit to the spectra, and it's a bit surprising. So that's why some people scratch their heads and make sure, is this really a good fit? It certainly looks like a good fit. It's hard to imagine what else these species could be. But the two really exciting species are that he sees in his data are H2, so that's molecular hydrogen, and also mercury. Um, and so what's fantastic is that if you go back in the literature, there's an article that was written, I think, a couple decades ago, actually. I don't remember the exact date, but it was, I don't remember the author off the top of my head now. I can dig it up and send that out to you, pass it around. But it was regarding the possibility of ice at or water at the poles of the moon, and it was titled "Don't Drink the Water." Maybe some of you out there know the article I'm talking about. And it was titled that because they speculated that there would also be mercury in the ices of the poles of the moon. And this was done a long while back. Um, but the H2, the molecular hydrogen, is really quite spectacular too, because that H2, as you might know, doesn't freeze out and stay stable for very long at even 40 Kelvin. It really is a volatile, and we're still speculating exactly how it is that it was trapped, in what form and what physical state, meaning was it in pores, was it actually, are there colder pockets within that 40K that can retain it? Um, and they saw a substantial amount of it. I believe Randy reported something like 150 kilograms or so total of H2. Um, the mercury is a very interesting too. Like I mentioned, you see mercury at Mercury, so maybe it's not all that surprising, but it was unexpected. No one was ready to say, "Aha, there's the mercury we were looking for." Um, and then in our own spectra, when you look at the ultraviolet visible spectrometer, the emission lines, all the emission and absorption lines just after impact, for the first 10, 20 seconds after impact, um, show a great number of different species. And uh, that combined with the number of absorbers that we see in the near infrared spectrometer really suggests that this part of Cabeus, at least, had been accumulating a variety of things that I think can't be all produced in situ chemically, that must be coming from either comet or asteroidal sources, in addition to the chemistry that can occur with just solar protons in situ. The reason I say that is because of the variety and the complexity and of some of these species. In addition, some of the mineralogy actually that we see perhaps in the dust itself that we kicked up suggests that it could be similar to what was seen by the M cubed instrument, but also maybe even more similar to what might be seen in aqueously altered asteroids, see chondrites and whatnot. So some of the kinds of things we think we see in the spectra range from, of course, water ice, but also carbon dioxide ice, CO2, SO2, hydrogen sulfide, H2S, methane, ammonia, methanol. These are all species that have found at least some indication are present there. It's really difficult when you get into these lighter hydrocarbons because there's so many various combinations that can produce various absorption bands. We have not identified every band in the near infrared. We've really focused on those associated with water and making sure we had a uniqueness that fit for the water vapor and water ice. Um, but there's certainly a lot of other things in there that are consistent with light hydrocarbons, cometary like material. In the ultraviolet visible, a lot of the emission lines we see are similar to what you would see, we think, in an impact of a comet, like deep impact, or just when you observe an active comet, some of the species coming off of that as well. So that was pretty one exciting to me and surprising. Lastly, one of the most pleasing aspects of this, and again, this is just my personal view right now. Before the papers are actually reviewed, they're submitted, and we're all very confident in the results. And one of the reasons why I'm so confident, and why what I say is so pleasing, is we had so many independent people approaching this problem from different angles, from the LRO side and the LCROSS side, and we found ourselves independently coming up with very consistent answers or measurements of various quantities, like the optical depth of the cloud or the potential concentration of hydrogen in the regolith. And on that last point, that was one of the final last, ooh, isn't that satisfying moments, was we came up with an estimate based on what we could see in our instruments on the concentration of dust in our spectrometer's field of view. And at first I was like, wow, it's kind of a high number. It's a lot, not necessarily what I expected. Did we do something wrong? Let's go back and look at this, and scrub the numbers again, and okay, well, we can't can't wiggle out of this answer. And then I saw the PI's Igor Munchunov, excuse me, PI for the Lend instrument came in with his paper, and it was entirely consistent with what we got in terms of concentrations in the regolith. So that was really exciting. That's one of those like, well, okay, not what we expected, but measurements. That's why you make measurements. um, and so where we are now is there's these 6 papers that are going in. A couple are actually going to probably one's going in finally this week, and that'd be 5 total, and then the 6th would be probably in a week. They're talking with the editor as to the timing of their review and hopefully their eventual publication. But we are making good progress in understanding the data, and I think we've probably scratched really just probably the top 10% of the data. There's a lot more information in there and a lot more we're going to learn when we combine all the observations, not just those from LRO and LCROSS, which are the ones we're keenly concentrating on now, but also the ground observations. The ground observatories did see a number of species that will really help constrain the vapor cloud and the presence of a number of refractory materials like sodium, potassium, and relevant to this H2 release that LAMP saw. So we're working all very closely with that. Going to a workshop in Boulder in a couple of weeks where we're going to present some more results and talk with the group there. It's a lunar atmosphere and dust workshop at the Laboratory of Atmospheric and Space Physics in Boulder, and where we're going to get together and talk about this stuff some more. One of the things that I think a number of us are thinking about doing is in about 3 or 4 months, getting a nice group of folks together with data observations and interest, and having a workshop on rebuilding the model for the polar cold traps, or at least the Cabeus, and extending that, of course, broadly to the moon in general, and really rebuilding a model of hydrogen transport, retention, evolution, etc., that I think is going to be substantially different than what we've come to so far. So it's going to be a really fun year or two actually going forward as everyone pulls this together, as the data both from LRO and LCROSS gets released to the public, so we can get a lot more neurons looking at this. It's really, I honestly think it's going to really revolutionize what we think about the moon and what we think about the activity of hydrogen currently and in the past on the moon right now. So with that, that's a quick brief summary. Like I said, it'd be maybe better. I'll leave it to you, Andy, as a moderator, to decide whether you want to throw out some general questions or just start taking some questions from the group. I could take the easy NASA employee way out. I do not speak to policy. No, I won't do that. That was actually at AGU. There was a session. I didn't, or I don't know if it was impromptu or what, but there was a panel discussion on this. I don't know if any of you out there were at it. I didn't. I was in a poster session. I missed it. Kim Eniko attended it, and she told me a little bit about it. And one of the questions was exactly that. Well, what do we do now? Do we send more impact missions to understand more sites, or do we go straight for the jugular and do sample return? As you know, New Frontiers did select a sample return mission. I don't know much about Moonrise. My understanding, though, is in the center of the Aitken Basin. The Aitken Basin does cut across the south pole of the moon, but the principal objectives per the New Frontiers call weren't related to volatiles. That said, it shows there's a keen interest in sample return from the moon, and the fact that one of the things I think that's coming out of both the Chandrayaan deep impact and Cassini measurements, along with the LRO measurements of temperatures and where hydrogen is, and LCROSS measurements is it may not be all that difficult to get to some places. You don't necessarily need a rover that goes into permanent shadow for a very long time to get some very interesting samples that could be returned or processed in situ to answer some, I think, really fundamental questions. Now, LCROSS was a real opportunistic mission. It took advantage of this extra mass that the LRO launch vehicle had, and then we took advantage of the launch vehicle itself uh, to actually just redo another mission to the moon. For example, could you do this with Grail? If Grail's going there on a Delta II, it's very hard to actually make work for the same cost. Now, LCROSS was about $79 million. It was a build to cost mission. I certainly think you can do inexpensive, low cost missions that could address a number of these. Take the next steps, either impact in different locations or even send a lander to a near shadowed region and study it. Um, uh, and that might be an excellent additional precursor to understand the distribution. Now the question is, how many do you need to do to actually really, before really say I understand the distribution? The alternative approach is to say, hey, we know where LCROSS hit. It is actually the LCROSS impact site is in view of Earth for certain librations. You can see it from Earth, and so it is completely reasonable to send something there and have communications with it to Earth. And it's showing the largest hydrogen deposits in the area from both Lunar Prospector and LEND data, pretty much. So it's another concept is to send in either a lander or a hopper or a rover and grab some material and either process it in situ or take it back. I think the key measurement that I would do is really mass spectroscopy, really get at what is the elemental breakdown and isotopic breakdown, what is the D to H, the deuterium to hydrogen ratio, that will, what is the carbon isotope ratio, the nitrogen, etc. That will really tell us the source of some of this water and hydrogen. Is it cometary? Is it asteroidal? Is it like a secondrite or what? Or does it look like solar from protons from the sun? And that would go a huge ways to really pinning down some of the questions that LCROSS, I think, has just raised even further. Um, Now, those are two. Sending a small lander or a small impactor is one mission flavor, and doing actually really in situ careful isotopic measurements is more like a New Frontiers mission. They're distinctly different. But I think both should be considered going forward, both either in a Discovery class or New Frontiers class mission like in SMD, or I would love to see ESMD do more missions, robotic missions. But that is not for me to decide. I was just lucky enough to get to participate in one of them. Yeah, good question. And that is what we saw in the field of view of our instrument. One of the things that the team, me in particular, maybe, is hesitant to do is at least at this point is do the complete reverse engineering of the impact and say, okay, from what we saw, this much total ejecta came out and excavated this much regolith, and it had this much stuff in it. Um, we took the easy way out, and what we did was let's just look at what we can see. And so that 100 kilograms or so of water which is about 26 gallons. It's been revised upward a little bit, not much, but certainly a little. It is what we could see in our 1 degree field of view, which was a good portion of the ejecta cloud. So it was, at least for periods of our descent, it was a good portion. It did capture most of what we could see in that ejecta cloud. But what we could see of the ejecta cloud is probably 1% or less the total excavated mass in the crater, perhaps. However, um, so, the way we approached it was we saw this much water in the field of view and we saw this much material, dust, debris in the field of view. What's the ratio of those two? And that's how we actually estimated the total concentration in the regolith. That number is in the 4 to 6% range right now, and um, but the that work needs to be done to really understand, okay, how does that relate then to more broadly what's in the regolith and how it's distributed in the regolith. And we think we have the data to answer that. It's just going to take, again, some more experiments like we're doing today. Pete Schultz and colleagues are doing that here at the Gun here at Ames, and also more modeling and more analysis of the data. So it's a long-winded answer for saying that was what was in our field of view. I again, we'll see if we convince the reviewers, but I think we've convinced pretty much everyone else who's seen the data right now. So um, uh, that was a big part of our goal, was to find a uniqueness. One of the great aspects of, I think, the measurements we took is we have multiple unique lines of evidence for water, and that comes from just direct near-infrared spectroscopic absorption, but also ultraviolet emissions from hydroxyl, which is typically the result of photolysis, and based actually on the temporal release of hydroxyl and water vapor that we see in the near-infrared spectrometer. Um, you can explain away other possible sources, like is it just adsorbed water from grains, or is it just OH being released from grains, or whatnot. You can actually um, uh, convince yourself that the best model is subliming ice grains. That said, we also get the best fits to our spectra right now, including water ice in the spectra. So I think, I'm very confident that the LCROSS measurements have very uh, uh, confidently, with a high degree of confidence, that we've detected the water for sure. The numbers may change here and there, and exactly how much, but it's I think it's in the right ballpark. What the number we have right now, we have some error bars, of course, associated with that. But as I said earlier, what builds my confidence is a lot of these separate measurements are all kind of holding together. We're not, and they're all worked independently, so we're not. There isn't any outliers, distinctly disturbing outliers right now in the data sets between either the LEND observations of neutrons, the LAMP observations, or LCROSS observations or diviner observations. They're all kind of just holding together. So that's making me pretty confident that this isn't. LCROSS set out to do what it was meant to do, was understand what that hydrogen is. That we knew it was hydrogen from the neutron measurements. I think LCROSS, the impact, along with its observations and LRO's observations, have done exactly what they set out to do, was understand what that hydrogen is. really now say, okay, we've got this much at this point, relate that to the hydrogen measurements, and then use LCROSS as a ground truth, and that's really what one of the goals at LCROSS, one of the things that LCROSS was going to be, was a ground truth for the hydrogen measurements. There's these great lunar prospector measurements of hydrogen, and there's these new measurements from LEND on LRO. They remotely sense hydrogen that can map the entire moon and understand how much hydrogen is with certain assumptions. We went to one spot and measured the total water there and can relate that to what they're seeing. And then you have to take the giant leap of faith and say, it's like that everywhere. Of course, it's not, but that's what you'd probably have to do at first, at least, to make it, assess the total inventory of water. Now, we haven't done that yet. Really, I can just talk about what's in the LCROSS site in terms of absolute numbers of water. But it won't be long before we can really make that estimate and give it a kind of an updated number to assuming 1% is, at 1%. My feeling is it's going to be pretty mixed. It's going to be pretty heterogeneous at scales of maybe a kilometer or two, um, and or even 100 meters or so, um, and so you know, understanding exactly what controls the stability of the hydrogen and or water or whatever else, whatever form the hydrogen is I think really going to be some of the homework we need to go forward, given these results, and understand to really accurately better assess the total water inventory at the poles of the moon. Based on some of the things I've seen from the land instruments and diviner instruments, it's not obvious, at least to me, that we understand exactly what's controlling the stability of these species. It's not necessarily just temperature, which is what you would, the zero order assumption would be. So we have to think about this, I think, a little bit more. You'd probably want to purify it if indeed, if the methanol and mercury findings stand up. Definitely don't drink it before purifying it. But that's a good question, and I think that's exactly the question in front of NASA right now. Given I can't speak to the policies, unfortunately, it's just not my job to do that. But it that's a good deal of water. If the values that we see in LCROSS hold up, um, and if the findings of LAMP hold up, you may not even have to, for example, disassociate the water to get the H2 out of it. I mean, there appears to be free H2 sitting there in the poles of the moon for people to utilize, future lunar colonists to utilize. Likewise, there's water. We've confirmed this, and uh, other very useful resources there. So I think that's definitely there. And like I said, maybe perhaps in pockets. I think it may not be very uniformly distributed, and not even distributed across from crater to crater. So that's one of the things that is actually startling me right now a little bit, is a lot of the measurements don't show that this is a completely uniform or equal opportunity process occurring between, say, Cabeus to Shoemaker to Shackleton, these various craters. But it certainly, one, makes it a very interesting place to go, the poles of the moon, from a scientific standpoint. But indeed, these findings show that the resources are there, that one could certainly, if nothing else, test some of the processes and tools and applications and technologies that may enable future missions to other worlds like Mars, or indeed help with a much more extended presence on the moon. I don't know anything about how it will lower the cost. but it may indeed enable some aspects of lunar either stay or colonization, or even other planetary um, exploration, like to Mars or beyond. Yeah, that's a really good question. It's typically what you'd expect is if you had a projectile hit rock, you get a very bright flash because you have all your energy coupling very nicely, and you get a lot of compactional and frictional heating, very high temperatures that go into this luminescence. Um, uh, in that case, however, you actually get not a lot of ejecta. Uh, if you have a projectile hit a fluffy, unconsolidated, loose soil, you'll have less flash as a little less at least, as the projectile does bury itself and deposits some of its energy at depth, not just at the surface. But then you've got all this, instead of going into fracturing rock, you have all the energy going into lifting that loose, fine debris. So you get actually a very nice plume. What complicated LCROSS is we didn't hit it with a simple projectile. We hit it with an empty rocket. So its mass density was not uniform. It was effectively low, quite low perhaps, maybe 0.03, 0.05 kilograms per meter cubed. I mean, it was a giant thermos bottle, right? Holding originally L2 and our liquid nitrogen and liquid oxygen. But so understanding how that actually uh, transfers its energy to the impact site as it crumples and buries itself. And it was slow. It was only 2.5 kilometers per second, which is very slow. Um, uh, so all that said, both the flash and the ejecta plume size and shape do relate to exactly what we hit. And it's the flash brightness as well as the timing of the flash relative to the impact time. And how much ejecta came up and how quickly lead us to believe that we had most of our material coming from a high angle plume, not the traditional kind of conical upside down lampshade ejecta cloud, and that we had very little flash due to the suppression of the flash by the one hitting loose debris with a low density slow object, but also by hitting volatiles and having a lot of that go into phase change. All that H2 and sodium and whatnot that we saw immediately upon impact, basically, um, uh, was changed from a solid to a vapor, and a lot of the energy went into doing that. Um, so uh, basically, we're doing some more experiments actually now, as I mentioned, to understand this, but they are related, but they're not maybe related in an obvious way. They're kind of two different effects from the experiment, this low density impactor experiment. Oh, we learn, don't we? From we, it's unfortunately what we've talked about this quite a bit on our team, of course, because we get asked about it quite a bit. Yeah, the predicted brightness of the plume I actually, working with some colleagues, generated some synthetic images that we posted. And actually, when I showed them to the team at large, they all kind of squinted and said, "I don't see it." I'm like, "Exactly. It is a graying of a black background, because you're exactly right. The dust grains, the lunar soil is dark. Our optical depths are very small. At most, 1 times 10 to the minus 3 optical depths, perhaps in the visible, in the column. So it's equivalent to about a magnitude 8 or a magnitude 9 stars, what we think we saw from our vantage point. So that's all. It's quite observable actually if you're looking in the right place. Um, the problem I think with the expectations was it got out of hand with artist renditions very early on. When you have an artist drawing a picture of an impact as seen if you were standing on the floor of Cabeus, it's an artist will anyone is going to want to draw that, make it look pretty cool. But as soon as that gets out, it kind of comes the standard and the expectation, and um, the fact that we were quote unquote bombing the moon, and we had to compete with Dave Letterman and everyone else. Once it became popular, um, it got out of it had a life of its own. That said, we could have managed that a lot better. We could have really said from the get-go, there, it's hard to observe anything on the moon from Earth, let alone a small impact. Get those simulated images out earlier, really get them in front of the press and in front of the public sooner. We should have done that to really manage those expectations better. On top of it, we moved from Cabeus A, which had the optimum Earth observing, to Cabeus, which had the worst Earth observing. 2 weeks prior to impact. That didn't help. It made the possibility of actually seeing anything from Earth very difficult. And that plus having we didn't of course on LCROSS have a second go at it. So all of our instrument settings and camera settings had to be set at a particular level. Only a couple of them could be streamed just from a technical standpoint, and the depending on what the commentator had up there, you did or did not see the ejecta cloud as faint as it was during the streaming video. So all that is again, next time we do this, we'll be a lot smarter in how we both show it off and set the expectations. Uh, One of the things that I like most about the LCROSS, and I think actually returns the most to the agency, NASA that is, and also though to the corporate industrial workplace, the people we work with, is the way LCROSS was done. It was an experiment into itself that could we build a mission that was truly built to cost, and that doesn't mean stay within a budget cap, but that means that the management of the requirements, the risks, and the goals, and how you achieve those goals are managed to stay within a particular cost box. Now, so for some, that may seem like, well, of course you do that. Well, that's not typically how projects are done. Typically, you have a requirement flow down from a measurement requirement or a performance requirement, and you build to that, and you set up a certain amount of reserve to cover it, a reserve amount of money to cover risk. Um, LCROSS actually had very small reserves going in, monetary reserves. We only had maybe 12 or 15%, if I recall. That's very small compared to more classic missions, which may have 25 or 30%. But we were designated Class D, and what that means is we could fail. Uh, and in terms of a risk, the way I like to think of it is on a Class D mission that can accept risk, you manage your risks. You say, these are all the risks I have in front of me. This could go wrong, this could go wrong, this could go wrong. Which is the worst? How much resources does it take to reduce the chance of that happening or reduce the impact of that? And let's use some of our limited resources to tackle that and then accept the others. On other projects, often it's not a management of the risk, it is a uh, beat down, a retirement of the risks. You have this risk, retire it. It's going to cost money, but we have to get rid of that risk altogether. That has schedule, it has cost, it has complexity often. LCROSS really performed in a way that allowed it to happen. I mean, it had to be these things because we only had 2.5 years to build the mission, fly it. We only had $79 million. That's very small, in today's project world for a lunar mission. Um, and also, the other aspect that I really think was key to success was credit to the project management on LCROSS and on LRO within NASA's Exploration Systems Directorate, and to our prime industry partner, Northrop Grumman. Um, this is the most open project I've ever worked on. People were so honest. The trust was built immediately, very openly. We had a very high level of engagement by the stakeholders at NASA to see what we were doing, how we were doing it, in part because it was such a crazy idea. I built this thing in 2.5 years for $79 million. But at the same time, that honesty, that openness, again, what it did was it just streamlined a lot of the processes that need to be streamlined, and that was one for me. That was actually one of the most rewarding aspects of this mission. So, getting back to your question, how does the United States or NASA, or close to my home, business-wise, benefit? I think we've actually developed or demonstrated, at least in one instance, a new tool that NASA can use and industry can use. I know that a great number of industry partners are looking to this to uh, to, to understand how it was done. Actually, Northrop Grumman retooled the entire way they do certain business lines to follow this model. And Northrop Grumman typically builds billion-dollar missions, not a $79 million mission. So this has really impressed them enough that they actually are building a new division around it. On the instrument side of things, which I was very hands-on with, I managed the payload and had very little bit of money. We had the payload budget was about 3.5% the total budget of the mission. That was the payload and science budget. Um, we worked with vendors out there, instrument vendors that provide commercial instruments, and made them flight qualified, and really again demonstrated that NASA can work with commercial vendors in an environment that had a bunch of give and take. Again, it was this open culture where we invited them in and they invited us in, and we just laid it out there and made it work. In one instance, I know the vendor has adopted a particular aspect of the process that we helped them develop and applied it to their entire product line. Other vendors have taken these, their new instruments basically that we developed, and one, it's a great marketing tool. Hey, I just built a camera that landed on the moon. But two, have taken the data that we were able to provide them through environmental testing and whatnot and apply it to their everyday product line. So um, in a way, it's kind of opened up a new way of doing business within NASA, and I think within the marketplace and how it relates to NASA. Yeah, I think the free molecular hydrogen, and a lot of it, 150 or so kilograms of it, is really surprising, and the amount of various species that appear to be in the data, meaning the not just the water, it's the potentially the CO2, the SO2, the H2S, the methane, the ammonia, et cetera, et cetera. It's that we these permanent shadows craters, these very cold craters, really have been collecting a lot of stuff over the last few billion years, or a few 100 million to a billion years at least. That I think is the most exciting and startling finding we've had so far. Uh, Honestly, it certainly exceeded them. Again, it's class. There were many times when we weren't sure we were going to have a payload on the LCROSS spacecraft. Our minimum success was to hit the moon in a way that it could be observed by Earth. Now, we would have probably hit someplace else if we didn't have a payload on the LCROSS, but that minimum success meant we didn't need all these instruments, this data that we're talking about. The initial position that LRO was going to take was on the other side of the moon to be safe. So you could imagine this could have turned out very, very differently. We could have impacted some. We would have relied entirely on ground-based observations, which would have really dictated where we were going to impact, even more so, to ensure good observations. And who knows what we would have gotten then. There was an incident, and just to show how sometimes luck has a lot to do with it. Back in August, we run the spacecraft autonomously when we were flying. Again, because you can't afford to keep people watching it 24/7, and we'd check in on it every 2 or 3 days to see how it was doing. And this is during the 4-month cruise after launch. And one morning, we had a planned maneuver, and we had some instrument activity that was going to occur. And this was the first time that I said, "Well, okay, I'm gonna sit this one out. It's 4 a.m. I need some sleep." The payload engineer went in along, and said, "Yeah, I'll call you if there's any trouble." Well, at 4 a.m., I get this phone call, and I said, "Oh boy, what's wrong?" And then I realized, well, wait, the instruments weren't supposed to turn on until 6 a.m. And that's when it struck us that we had a real problem. And I hurried up and I got into work and into mission operations. And the team had declared a spacecraft emergency. Turned out that we got into a quirky little autonomous software state because of a single bit fault on a navigation instrument, and our little spacecraft was trying to control itself to some navigation noise on one of the instruments. This was detailed pretty well in a blog by the flight director, Paul Tompkins, and it spent a lot of its fuel trying to do what the software was telling it to do. Well, it turned out if we had come in maybe 2 hours later, it would have been out of gas, and we would have had a mission. So we got that close to having a problem, but we got in there. The team made the quick assessment, stopped the bleeding, and then slowly brought it back up to good health to complete the mission. I mean, so yeah, it beat expectations, I think, by everybody, right? I think at first, no one thought we'd even make it to the dance, meaning the launch. Two, I don't know that anyone believed we'd get there in one piece. Myself, we had multiple cameras, not necessarily to have multiple filters, but to have redundant cameras because we figured we'd lose one or two. Well, we didn't lose any of them. We had the full instrument set. We had the full LCROSS. 2 weeks before impact, I was still talking with the LRO systems engineers and our science team, convincing them it was safe to have this close approach. They decided on it. Then they did the phasing burn just 2 weeks prior or so, and so it all came together in the end. And yeah, these results I think have really just blown everyone's expectations of what we would see out of the water. No pun intended. Yeah, thank you, Andy. It was great.